Section 4.2 is about one-to-one functions and inverses. A function f from a to b is said to be one-to-one if each x value has exactly one y value and each y value has exactly one x value. So here's an example of a one-to-one function. Here's an example of a function, right? Each x has exactly one y value, but this is not a one-to-one function, but it is still a function. So that's good to know. So the way we test if something is a one-to-one function is the horizontal line test. So the first things first, you have to check that you have a function. Remember, we check that we have a function using the vertical line test. So all of these pass the vertical line test. We then use the horizontal line test to determine if each x has exactly one y value. So this right here is a one-to-one function, but the rest of these are not one-to-one functions. And if it's not a function, it's not going to be a one-to-one function. So there you go. What's really cool about one-to-one functions is if f is a one-to-one function and g is the inverse, right? That means it's reflected across the y equals x axis. Then f composed with g will equal x and g composed with f will equal x, right? All one-to-one functions have inverses. So let's look at these two functions defined as relations. We're going to identify their domains and ranges and determine if they are in fact inverses. Remember, for something to be inverse, their x and y values are swapped. So for example, if I had the point when x was 1, y was 3, then over here I'd have the point when x was 3, y was 1. Our domains and ranges are swapped. So here for the domain of f, let's look at f. I've got all my x values, which are -2, -1, 0, 1. And I have a range of when y, right? Our ranges are y values. I've got a range of 2, 1, 0, 3. Now let's look at g, because remember we want to see if the range of f becomes the domain of g. That would help us tell if they were indeed inverses. So my domain in this case is 2, 1, 0, 3. And my range is -2, -1, 0, 1. So as you can tell, if the point, AB is on f, then BA is on G, right? They changed places everywhere. So these two functions defined as relations are in fact inverses. So let's see if these two functions are inverses. To determine if they're inverses, we're going to have to do function composition both ways and see if we get x. If we don't get x for one of them, we can stop, and then we know they aren't inverses. So if I have f composed with g of x, that's -3 of -1/3 x minus 12 plus 12. That gives me a positive x minus 36 plus 12. Okay, that gives me, positive 36, because two negatives make a positive. That gives me x plus 48. That does not equal x, so these are not going to be inverses. And I don't need to check g composed with f, because I already know they aren't inverses. Let's take a look at another example. How do I find the equation? Did I miss an example? Oh, I'm sorry, I did. So let's determine if these two functions are inverses. I have f of x equals x cubed minus 1 and g of x equals the cube root of x plus 1. I'm going to go ahead and take f composed with g of x. So that gives me the cube root of x plus 1 cubed minus 1. That's going to give me x plus 1, because cubes undo cube roots, minus 1. So x. So f composed with g does equal x. Are these inverses? I don't know. I have to check g composed with f first. And that's how I want you to show this on an exam. So I've got the cube root of x cubed minus 1 plus 1. That gives me the cube root of x cubed, which just gives us x. So these functions are in fact inverses. Okay, now what if I wanted to find the equation for an inverse? So if I have a one-to-one function, so you first got to check it's a function, then you got to check it's one-to-one, but then what you do is interchange your x and y, solve for y, and replace y with f inverse of x. So I have f of x equals 2x plus 5. So that's y equals 2x plus 5. I change my x and my y, and then I solve for y. So this right here, this is my inverse. So I write f inverse of x equals 1/2 x minus 5/2. And I knew this was a one-to-one function because this is a linear function. If I have f of x equals x minus 2 cubed, this is a function that looks kind of like this, and it will pass the vertical line test to be a function and the horizontal line test to be a one-to-one function. So I'm going to rewrite this as y x minus 2 cubed. We interchange our x and y, and then we solve for y. I'm going to start by taking the cube root of both sides. So I have the cube root of x equals y minus 2. I add 2, so I get the cube root of x plus 2 equals y. So that means f inverse of x equals the cube root of x plus 2. Now, in class, I talked about how these functions did not have inverses. Well, because they're parabolas and they fail the horizontal line test. However, they can have inverses if we restrict their domains. So let's find the inverse and then see how we'd have to restrict the domain. Right now, both these functions have domains from negative infinity to positive infinity, but the domain of its inverse isn't going to be that, and let me show you why. I'm going to go ahead and interchange my x and y, and then I go about solving for y. I get x minus 2 is y squared, square root of both sides. So I have y, which is f inverse of x, equals the square root of x minus 2. Now this domain, right, this domain isn't going to be the same as for the domain of our original function, because square root of x minus 2 has to be positive. So in this case, this domain is restricted as long as x is greater than 2. So the domain is restricted from 2 to infinity. Let's try this again. I have y equals x squared minus 4. X equals y squared minus 4. I go ahead and add 4 to both sides. X plus 4 equals y squared. I take the square root of both sides. So I have the square root of x plus 4 equals y. So that's my f inverse. But again, its domain isn't going to be all real numbers. Its domain, because this graph has been shifted to the left, its domain is going to be from negative 4 included, because the square root is 0, 0, all the way to infinity. So even though these aren't one-to-one, they can have inverses over restricted domains. Some important facts about inverses real quick is that if f is one-to-one, it has an inverse 100%. The domain of f is the range of f inverse, and the range of f is the domain of f inverse. If AB lies on our point f, then BA lies on our point f inverse, and these two graphs are a reflection of each other across the y equals x axis.